Hello friends, today we start with second unit of our syllabus titled as Current Electricity. It is the third chapter of our book. Now, what is current electricity? Let us define. The branch of physics which deals with the study of electric charges in motion is defined as current electricity. I repeat, the branch of physics which deals with the study of electric charges in motion is called as current electricity. An electric charge in motion is denoted by small q, whereas static charge is denoted by capital Q. Now mind map of the unit, how we are going to learn this unit. So there are big 7 topics. First topic is Ohm's law, second is color codes, third is series parallel combination of resistances, fourth is Joule's law of heating, fifth is Kirchhoff's laws, sixth is measurement of resistance, where we are going to study about Wheatstone bridge and meter bridge, and seventh is measurement of EMF, where we are going to study about EMF equation of cell and measurement of its EMF with the help of potentiometer, etc., etc. Now, in order to understand Ohm's law, there are certain preliminary terms which we are to understand. First one is current flow through conductor, second is types of electric current, third is motion of electrons in conductor, fourth is electromotive force or EMF or electron motion by force, fifth is electric current density, sixth term is drift, and seventh one is relaxation type, eighth is drift velocity, ninth is mobility, 10th is relation I is equal to NEVDA, 11th is J is equal to NEVD, where J is current density. Now in this we will be studying first 5 in the part 1, preliminary part 1, and first 5 are current flow through conductor, types of electric current, motion of electrons in conductor, EMF, electric current density. And the other 6 we will be studying in preliminaries part 2, that is drift, relaxation time, drift velocity, mobility, I is equal to NEVDA and J is equal to NEVD. So in 2 different parts we have divided these 11 terms in preliminary part 1, 1 to 5, and preliminary part 2, 6 to 11. Now we start with current flow through conductor. First term, current flow through conductor. First part of it, electric current flow. How electric current flows? Let us see, try to understand it. First, electric current flow. As water flows from higher level to lower level, heat flows from higher temperature to lower temperature. In the same way, electric current flows from higher electric potential to lower electric potential in a conductor, as shown in diagram. I repeat, as water flows from higher level to lower level, heat flows from higher temperature to lower temperature. In the same way, electric current flows from higher electric potential to lower electric potential in a conductor, as shown in diagram. Here, point A is at higher potential and B is at lower electric potential. Here current I flows from positive terminal of battery through conductor to the negative terminal of the battery as shown by a red arrow. So this is how current flows from higher electric potential to lower electric potential. We will learn in more detail in the next slide. Example, a conductor AB is connected across a battery as shown, and A is connected to positive and B is connected to negative of battery B dash, and A is at higher electric potential being positive and B is at lower electric potential being negative. Therefore, electric current flows from end A to end B of the conductor, that is from positive terminal of battery through conductor to negative terminal of battery. The flow is denoted by an arrow. 2. Definition of electric current. Rate of flow of charge through a particular area of a conductor is defined as electric current. I repeat, rate of flow of charge through a particular area of a conductor is defined as electric current. 3. Mathematical expression. If Q be the electric charge that flows through a conductor for time t, then electric current through the conductor is, say, I equal to Q by T. 4th, SI unit, coulomb per second, or C sec inverse, or ampere. 5. Definition of ampere. Since I is equal to Q by T, and if Q is equal to 1 coulomb, T is equal to 1 second, then I is equal to 1 coulomb divided by 1 second, or it is equal to 1 coulomb per second, or 1 ampere. Now let us define. Current flowing through a conductor is said to be 1 ampere when a charge of 1 coulomb flows through it for 1 second. I repeat, current flowing through a conductor is said to be 1 ampere when a charge of 1 coulomb flows through it for 1 second. Okay, this is how we define ampere. 6th, type of quantity. Electric current is a scalar quantity. The arrow in the circuit shows the direction of flow and not electric current. I repeat, arrow in the circuit shows direction of flow of positive charges only, and it is not a vector quantity. Assignment 3.1, question number 1. Calculate number of electrons flowing per second through a conductor when 1 ampere of electric current flows through it. Your answer would be 6.25 into 10 raised to power 18 electrons. Now second, types of electric current. First, direct current or DC. The electric current whose magnitude and direction both remain same with time is called as direct current or DC. It is denoted by capital I. Now here in the graph you can see here is the current along positive y-axis and time is along positive x-axis, and the magnitude remains same, constant with time. So it represents direct current, DC. Now we come to second, alternating current or AC. The electric current whose amplitude varies with time and direction changes periodically is called as alternating current or AC. It is denoted by small I. Now in this graph you can see current I small is represented by small I along positive y-axis, and time is represented along positive x-axis, and the electric current is whose amplitude is varying with time, and direction is also changing periodically. So this graph represents AC. 3. Steady current. If magnitude of current remains constant with time, the current is said to be steady. So here in this graph you can see the magnitude of current is constant throughout. So this represents a steady current. 4th, varying current. If the magnitude of electric current varies with time, the current is said to be varying current. Now in this graph you can see current is increasing with time, and in this graph current is decreasing with time, and in the third graph both type of current have been represented. So up to this point the current is varying, and up to this point current is steady because this region is varying current region and this region is steady current region. 5th, instantaneous current. The current flowing at any instant of time when flowing current is varying or changing with time, as shown in figure A. Here current I is represented along positive y-axis and time along positive x-axis, and the current is varying with time. So at any particular time the magnitude of current is this much. So this current is called as instantaneous current. Now if rate of flow of charge varies with time, then instantaneous current is given by the expression IT is equal to dq by dt, as shown in figure B. Let us mark this as equation 1. 6th, conventional current. The flow of positive charges from positive terminal of battery through conductor to negative terminal of battery is called as conventional current. So look at the diagram. This diagram, the circuit contains a conductor connected to a battery, and electric current is flowing from positive terminal of battery through conductor to negative terminal of the battery. So we call it as conventional current. 7th, electronic current. The flow of electrons from negative terminal of battery through conductor to the positive terminal of battery is called as electronic current. Here you see in the diagram, this is electron, and this electron is accelerated by the electric field due to the battery applied to the conductor, and it experiences a force F is equal to small e into capital E, and it is moving from a negative terminal of battery through conductor to the positive terminal of battery. So we call it as electronic current. Electrons flow up in opposite direction to the conventional current. Okay. Now we come to the third term. Third, motion of electrons in conductor. First, random motion. A metallic wire contains a large number of electrons moving in random directions, as shown in diagram. Such electrons are called as free electrons. The electric current through such a conductor is zero, because number of electrons crossing a particular cross section in one direction is equal to number of electrons crossing the same cross section in opposite direction. So therefore electric current through the conductor is 0. I repeat, a metallic wire contains large number of electrons in random directions. Such electrons are called as free electrons. The electric current through such a conductor is 0 because number of electrons crossing a particular cross section in one direction is equal to number of electrons crossing the same cross section in opposite direction. So therefore net current through the conductor is 0. 2. Directed motion of electrons. When electric field E is equal to V by L is applied across the conductor, electrons acquire directed motion in the direction opposite to applied electric field as shown in diagram. So this is the direction of electric field and the electrons are moving in opposite direction. So when field is applied, electrons are accelerated and they experience a force F is equal to small e into capital E, where capital E is the electric field and small e is the charge on an electron, and they are accelerated through the conductor in a direction opposite to the applied electric field. Okay. Fourth, electromotive force or EMF or electron motion by force. The external force necessary to make 6.25 into 10 raised to power 18 free electrons move in a definite direction across a conductor is called as EMF, or maximum work done in taking 1 coulomb of charge once round the circuit is defined as EMF. Mathematically expressed as VA minus VB is equal to WBA by Q naught, where VA is electric potential at end A of the conductor, VB is the electric potential at end B of the conductor, and WBA is the work done in bringing a negative test charge from end B to end A. Now question arises, where from the external force comes? The external force comes from the cell providing the applied electric field. Also, EMF is defined as the terminal PD of the cell in open circuit and is denoted by capital E and is always more than V. E is always more than terminal potential difference V. Now SI unit of EMF. Volt is the SI unit of EMF being terminal PD. Fifth term, electric current density. First definition, electric current flowing per unit area of cross section of a conductor is defined as current density. I repeat, electric current flowing per unit area of cross section of a conductor is defined as electric current density. 2. Mathematical expression. If I be the electric current flowing through a conductor of area of cross section A, then current density J is equal to I by A. Third, SI unit, ampere per meter square, or A M inverse 2. Assignment 3.1 continued. Question number 2. Define the following terms with reference to current flow through conductor and give their SI units. Number 1, EMF. Number 2, current density. Thank you so much. Next time we'll take up part 2 in continuation with preliminaries. Thank you so much. Till then, goodbye.